So we are poised right now to go directly into the nomenclature of alkanes, but just as a little review, where we left off last time, as we sort of moved into this idea of alkane nomenclature, we had to separate the idea of the parent structure and substituents, and we named a number of parent structures and as well as a number of substituents. There were either alkyl substituents or halide substituents. Halide substituents were fairly straightforward. They were just any of our halogens, but we take, in order to name them, we take the prefix, like chlorine would be chlor, and then put an O at the end. Chloro, or fluoro, or bromo, or iodo. We spent significantly more time on our alkyl substituents, methyl, ethyl, propyl, isopropyl, and so on, but we did manage to get the nomenclature of them down, as well as what we left off with was their classification. So now we're going to bring it all together. So this is best done in sort of a learn by doing method, and it's just best to throw out a structure and name it using these IUPAC rules. So we'll try to present these rules slowly with ever increasing challenge level on what we're being asked to name. But down in the lower left-hand side, we have a structure here. And how do we name that? Well, we know that it is a combination of a parent structure and whatever is not parent structure is substituents. So the first thing to do, as we looked at before, at least rudimentarily, is to determine the longest continuous chain of carbons in the structure. That will be the parent chain. So really, we have to try all possibilities here. 1, 2, 3, 4. 1, 2, 3, 4. And we end up with what would be the actual longest one, 1, 2, 3, 4, 5 carbons. 5 carbons. So that is the parent structure. So 5 carbons we know as a parent structure is pentane. Now the parent structure name always goes on the end, the very end. We always name these things from the back to the front, whether we're going from structure to name or name to structure. So we put pentane all at the end. Next, we have to number that parent chain. And we number it, it's either going one way or the other. We could number the parent chain 1, 2, 3, 4, 5 this way, or 1, 2, 3, 4, 5 the other way. Which end do we start on it? And understand, as we number these, we're going to be giving each carbon atom in the parent chain a particular number. So because we have an open chain, which way do we start? Well, we number in the direction which gives the lowest numerical designation for these substituents. Notice, if we started over here on the left-hand side and made that the 1 carbon, well, that would make this one the 2 carbon, the one that the bromo is on, and this one the 3 carbon, the one that that methyl group is on, 2 and 3. Well, what if we went from the other direction and made this one our 1 carbon? Then we'd have to count 2, 3. So the methyl now is on the 3rd one, and the bromo is on the 4th one. Those are larger numbers. So we have to start with the lowest numerical designation, which is from left to right in this case. It's important that you see that distinction. So we number these carbons from the left to the right because it gives the substituents the lowest numerical designation. Now, everything that is not parent structure must be substituents. So we have to name these substituents or determine the names of them, or at least identify them. So here we have a methyl group and a bromo group. Importantly now, so how do we sort of cast this all together to reel this in? These substituents, if we have more than one substituent, they have to be placed in alphabetical order. So along with the number of each carbon atom that they're attached to. So notice here we have B in bromo comes before M in methyl. So thus we are going to name that bromo first, or put it in the name first. And it happens to be attached to, notice which carbon it's attached to, is the 2 carbon. So we would put 2 bromo, then at the 3rd carbon, we have a methyl group, 3 methyl. Now, so 2 bromo, 3 methyl pentane. We had to do those in alphabetical order. Now look very carefully. We use a lot of dashes in here. 2 dash bromo dash 3 dash methyl pentane. So we have to separate a lot of these things, especially between numbers and substituents, with dashes. It's not just all numbers and letters squished together. We have those dashes thrown in there. Let's look at another example. So importantly, this is a two-way street. On the previous one, we were given a structure and we were asked to deduce the name, the nomenclature of that structure. We can also turn this around, and we can be given a name and be asked to draw the structure. In my experience with these with nomenclature problems, it is much more straightforward, I hesitate to say easy, but more straightforward if given a name of a compound to draw the actual structure, because we're afforded more freedoms, and as we move forward, perhaps we will see why. Now, importantly, just as in the last problem, we had to start back to front, it's even more important now when given a name of a compound. Going to structure, we have to start from back to front. So the very last piece we have on this very long name is octane. That is our parent structure, octane. So that is an 8-carbon alkane chain, an 8-carbon. That was octane. So we're just going to draw that. And there's my octane. And in this case, we always have to number the chain, but notice on number 2 up here, it says we have to number the parent chain from the end, which gives the substituents the lowest numerical designation. We don't have to worry about that when we're going from name to structure. We can start drawing or start numbering that any way we want. We could number from the left-hand side and go right, or number from the right-hand side and go left. It will not matter. So in this case, let's just start from the left, go to the right. We number all of our carbons 1 through 8. And then we go back and look at the name and notice that we have a number of different structures. Here we have methyl, we have a fluoro, we have an ethyl group, and we have their addresses. That methyl is going to be on the 3-carbon, the ethyl is going to be on the 5-carbon, and the fluoro is going to be on the 1-carbon. So slowly drawing these in, it just becomes like following a recipe for baking a cake or something like that. It's much more straightforward. We don't have to deduce which way we're going to be numbering and, okay, which substituent goes with what number, and putting it in alphabetical order as we did going from structure into the actual name. This gives us a lot more freedom to move forward. So let's look at another example. Now, some of these it can get pretty hairy if as they start to become more and more complex. So here we have a system where we have a structure and we're being asked to give its name. So in this case, we have to determine the parent structure. Now, don't be fooled, because it's very tempting to just pick out as a parent chain that one zigzag going in in a horizontal direction. So that's 6 carbons, that would be a hexane, right? Very, very tempting to do that. However, we have to try all possible values, and we find that that is not the longest continuous carbon chain. We actually have a longer chain if we look through that carefully, and if we sort of meanders around, but that is indeed the longest continuous parent chain. It turns out to be 7 carbons, so that is our parent structure, heptane, and we put that at the very end, as we saw before, the heptane. Now, everything, I've sort of made that in red, that parent chain on my structure. Everything that is not parent structure is now substituents. And we have a lot of substituents here. We have a couple of bromo groups, we have a methyl group, we have an ethyl group. But before we even get into that, it's important to number this parent chain from one end or the other. And the trick was to number it that gives the substituents the lowest numerical designation. This can be difficult with a lot. We have 4 substituents here. So we have to try it both ways. If we went from the left-hand side on this, I would notice that I would have, starting over here, I would have substituents on the 2, 3, 4, and 5 carbon. 2, 3, 4, 5. So I can add those numbers up and get another number. Fair enough. 14. 2 plus 3 plus 4 plus 5. Let's try numbering the other direction. So over here on the right, we said this is our 1 carbon, there's our 2. So we have substituents on the 3, the 4, the 5, and the 6 carbon going this direction. So that would be, if we add those together, 3 plus 4 plus 5 plus 6 is 18. So here's, now that we have both of those, we choose the direction which gives the lowest number. That would be the direction which gives us 14 in this case, and that is how we're going to number it, 1 through 7. Seems like it's a lot, and sometimes you can figure this out on your own if there's only 1 or 2 substituents and they're all the way over to one side of the parent structure. It's like, all right, yeah, I'm going to name, or I'm going to number from that side. Sometimes you have to do what I just did here, just as a check to make sure you're numbering in the right direction. Because if you're not, then every single one of your substituents is going to have the wrong number, or most of them anyways. So, having numbered this correctly, now we look to our substituents. What do we have here? Well, I see, as I said before, a couple of bromos, there's a methyl, there's an ethyl, and now I introduce one of our little idiosyncrasies in the IUPAC nomenclature of alkanes. If we happen to have multiples of one substituent, we don't say 2-bromo, 3-bromo, we condense that into, use a Greek prefix. Since we have 2 bromos, it's considered sort of together as a dibromo. Now, interestingly, and we'll get into this in the next example, so it's not bromo, it is dibromo with a D. That di is a modifier. Now, modifiers, it won't matter in this case, but modifiers, the di and dibromo, are not included in the alphabetical placement. Interesting. But it won't matter in this case, but we would go with the B in dibromo, not the D in dibromo, just to make it much more complex, of course. But in any case, so we have dibromo, and those 2 bromos happen to be at the 2 and the 3 position, followed by, so we did the B in bromo. We're going to do those first in this name. Then we go to the E in ethyl, is next alphabetically. It happens to be connected to the 4 carbon. And then the M in methyl, which happens to be connected to the 5 carbon. So we're going to put this together. We'll start with the B in dibromo. 2, 3 dash dibromo dash, what was next, ethyl, 4 ethyl, and then 5 methyl heptane. That's a mouthful. The only way to really do this effectively and easily is to bust it up into manageable chunks, which is what we just did. Parent structure, numbering direction, what are the substituents, what's the alphabetical order, then put them all in a row. Remember, we started way over on the end with the parent structure heptane, and then front-loaded it alphabetically with all of our substituents, which we see here. So let's look at another example. I'm a firm believer in multiple examples are better than fewer examples. If you're bored, you're welcome to fast forward through this. But when you have something as as intricate and with as the IUPAC nomenclature for alkanes, and that has so many U-turns and rabbit holes and little idiosyncrasies, it is important, I feel, to have a greater number of examples as we move forward in order to master it. So we have here a structure which we're going to be asked to name. If given a structure, have a name. So now we have to find the longest continuous carbon chain, which is going to be our parent chain. In this case, it is a little bit more predictable. It is indeed that horizontal zigzag for 10. We count 10 carbons, which gives us a decane. Decane is our parent structure, 10 carbons. Remember, I won't have you name anything whose parent structure is longer than 10 carbons, so this is the limit. And we find that now that we've identified the parent structure, we have some substituents. Where are those substituents located? Well, we have to number the chain. In this case, we have to be careful. It may be a little more obvious this time as to which way you would start numbering from, but it's always to give the substituents the lowest numerical designation as with respect to the carbon atoms they're attached to. We'll do it both ways just to be sure. So if we started over on the left, here is our 1 carbon. We would have we would go down, we have substituents at the 2 and the 6 carbon if we were going in this direction. So 2 plus 6 equals 8. So let's go from the other side. We have from our right-hand side, we would notice that we would have substituents for the 5 and the 9 carbon. In this case, 5 plus 9 is 14. Which way do we start from? From which direction? Well, the one that gives the lower sum in this case. So we would number from left to right in this case. Now that we've numbered, we have addresses for each of our substituents, and we have to be able to identify them. So we have turns out we have a methyl substituent and a tert-butyl substituent. These are examples of alkyl groups that we went over in the last lecture. And now we have to arrange these alphabetically at the front end of the name. Now initially, it sort of seems like the M in methyl comes before the T in tert-butyl. However, the tert in tert-butyl is a modifier. We have to go with the B in tert-butyl. And the B in tert-butyl comes before the M in methyl. A little tricky there. So the tert-butyl group is done first, and that's at the 6th position, and the methyl is at the 2 position. 6 tert-butyl, 2 methyl decane. Notice where we have to put some dashes in there to separate the numbers and the names. But once that is mastered, we have effectively named this structure. Here's another way of coming at this this nomenclature business. What if we're asked to determine the veracity or the truthfulness of a particular name, such as the following? Is the following IUPAC name correct? 2,3-diethylbutane. If not, give the correct name. There's really no way to figure this out because it seems correctly. No way to figure it out other than drawing this. Let's draw 2,3-diethylbutane. And if we draw 2,3-diethylbutane and name it according to the rules of IUPAC, let's see if we have the same name. So let's draw that. There's butane, 1, 2, 3, 4 carbons, carbons at the ends and the bends. And now at the 2 and the 3 position, let's put on some ethyl groups. There's 1, 2, 3, and 4, and there's our ethyl groups on there. Is this a correct name? The only way to find out is to name it again. We would find that in this case, there's actually a longer parent structure than 4 carbons. In fact, we find that is 6 carbons long if we trace it that way, which makes it a hexane. And there are what's left over are actually 2 methyl groups at the 3 and the 4 position if we numbered it. So it comes out to 3, 4 dimethyl hexane now. Really, the only way to solve this sort of problem is to do exactly as it says here, draw it out and name it again using the rules of IUPAC. Is it the same name? If it is, great. If not, then that's the actual name that we're given. Here's another one. In this case, how many of the structures below would have the name 2, 3, 5 trimethyl heptane? Notice in that name you don't actually say the commas. It's just 2, 3, 5 trimethyl heptane. And in this case, wow, this is a little bit of a tricky one. And really the only way to do this is to name all 4 of these compounds by using the rules of IUPAC and see if any of them come up with the name 2,3,5 trimethyl heptane. We're using those Greek modifiers now. There's 3 methyls, trimethyl, and notice there's 3 numbers there. Well, longest continuous carbon chain on each of these, we would be able to work out, and in each case, that is the longest continuous carbon chain. It's 7 carbons. Heptane. Okay, so they're all heptane. We can't exclude any of them, and we have to number each of these from the direction that gives the substituents the lowest numerical designation. And we would find out that this is how this would work. And now look at that. We have parent structures and methyl groups on each of these. Look at where each of these methyl groups, what carbon numbers they're attached to. We find these 3 methyl groups all attached to the 2, the 3, and the 5 carbon. So the answer, how many of these structures below would have the name 2,3,5 trimethyl heptane? Well, all of them. They're all different ways of expressing 2,3,5 trimethyl heptane. And this is a very good lesson as to how organic chemistry differs from general chemistry. One of the real pieces here is that these are at least the way they were given before, perfectly reasonable representations all of the same compound, but they look very different. As a matter of fact, they all look like spider webs until you can tease them apart. Each one, we were able to determine the parent structure, determine the proper numbering, and then slowly come to the conclusion and say, wow, they're all reasonable representations of the same structure. So let's move now into back when we were looking at carbon compounds, there was one sort of special way that carbons could come together that's different than these linear or branch structures, and that was with respect to a cyclic structure. If we had all the carbons in that parent structure or in that structure put into a cycle. There are alkanes of various carbon number, but with the carbon atoms forming a cyclic structure. So let's look at some of the representative parent structures we've looked at before: propane, butane, pentane, and hexane. These are our parent structures written in line drawing. I know they're the proper number of carbons, 3, 4, 5, 6, because I can count the number of ends and bens in each structure, and I come up with the appropriate number. So, for instance, a cyclic structure of 6 carbons would have to have the word hexane in it. A cyclic structure of 4 carbons is still 4 carbons, so would have to have the name butane in it, and so on. So we work this out such that we put a modifier on there, and that modifier is cyclo. So for instance, propane over on the left-hand side, if we put those 3 carbons together in a ring, becomes cyclopropane. Not cyclic propane, cyclopropane. And this starts to look like we're in geometry class again. It's like, well, we just drew a triangle in line drawing. So these look like geometric shapes, really, as we move across. The 4 carbons in butane, if we put them together, becomes cyclobutane. It's like, well, looks like we just drew a square and indeed you did, but all those 4 bens in there are carbons. 5 carbons in pentane become cyclopentane, and the 6 carbons in hexane become cyclohexane. So these are a new breed, if you will, of new parent structures that we can use when naming compounds. Let's look at an example, because sometimes we have to be a little careful in discerning a parent structure when we have, say, a cyclohexane with a methyl group on it or an ethyl group on it. Where is the parent, and what is considered the substituent? Let's take a look. Here we have a cyclic structure now with some sort of a protuberance on it. How would we name this? And the first thing we do in alkane nomenclature, whether it's cyclic alkane nomenclature or linear, is to discern a parent structure. So I'm going to tell you what you never, ever want to do in nomenclature, ever. Never count from a ring to from the inside of a ring to the outside, or from the outside of a ring to the inside. You will get it wrong. For instance, if I looked over on the right-hand side of this and started numbering, it's like, okay, I think I'll start numbering here. 1, 2, 3, 4, 5, 6. Oh, you're already doomed. You're already doomed. Because you notice you went from the outside of a ring to starting to counting the ring carbons themselves. They have to be kept separate. In fact, we have to be able to discern the parent is either going to be the cyclic structure or in this case, the substituent on it. We have to make a demarcation line. That separates the difference between this cyclic structure of 8 carbons, I know it's 8 carbons, cyclooctane, because it looks like a stop sign, from the other carbons outside of it, 1, 2, 3. We have to keep them separate. Very important that red line that I just drew there separates the two into a linear component or a non-cyclic component and the cycle itself. So this also allows us to now bring into play or to discern which one is the parent structure. Before, we had looked at parent structure as the longest continuous carbon chain. Well, now that we're dealing with cycloalkanes, it's not always a chain, meaning it has a beginning and an end. The parent could actually be the cycle itself, which does not have a beginning and an end. And that's indeed what the case would be here. The 8 carbons in the ring, which is cyclooctane, is more than the 3 carbons in that substituent that we delineated before. So that cyclooctane has the greatest number of carbons. So that's the parent structure. And we put the name of that parent structure at the end. So there it is, cyclooctane. Be careful, it's called cyclooctane. If you look at it sideways, you can think it's cycllolkanes. But all the organic chemistry jocks would think you were kind of stupid, and that wouldn't be cool. It's cyclooctane. In any event, cyclooctane is our parent structure, but now remember, once we identified our parent structure, we had to number that parent structure from a particular end. Well, it doesn't matter in this case. Notice that this group that I see right here of 3 carbons, I could, if I wanted to, hang that off of any carbon on this cyclooctane, and it would be the same structure. It's important to be able to see that. I could just turn this structure around and have that 3 carbon piece anywhere I wanted to. Now, if there's only one substituent, let me just clean this up a little bit. If there's only one substituent in this case, which there is, we don't have to number the ring carbons like we had to number a normal parent structure. We don't have to do it, because we don't have to say, for instance, that this would be 1 cyclooctane with our 1 right there, because if I just turn the structure, well, that 1 could become 3, could become 5. It is always 1. and thus redundant. So all we have to do is recognize what this structure is. Well, it happens to be 1, 2, 3 carbons on it. 3 carbons is in a chain is a propyl group. So a propyl group, we're just going to put propyl on the beginning of that name. Propyl cyclooctane. That's it. Doesn't have to be, for instance, 1 propyl cyclooctane, because they're all 1 on that ring, because the ring has no beginning and no end. So I could rotate that ring such that I could put, as I said before, put that propyl group on any of them, and it really would not matter. So just propyl cyclooctane. Okay, so what if we have a what is clearly a cyclic parent structure, but there's more than one substituent on it? In this case, we have a couple of chloro groups on a cyclic structure. Well, that cyclic structure has 6 carbons on it, so that is cyclohexane. There's no other carbon shrubbery on there, so we don't have to worry about, well, is it which is the parent structure and so on. It's cyclohexane. So now that we have that the parent structure, we have to look to the substituents and how they're arranged on the ring. If there's more substituent on a ring, the ring now must be numbered in order to show the relative placement of those substituents on the ring. On here we can see that they're adjacent to one another, but I could put 2 chloros on cyclohexane so that they're across from one another, or on the next carbon over, or something like that, all of which would be different compounds. So we have to, so how do we do this? The ring must be numbered. Where do we start numbering? Where's the 1 carbon on a ring? Because a ring, it has no beginning and no end. How do we discern that? We know it's cyclohexane. We've already discerned that's the name of the structure, but now where do we put that 1 carbon? Well, here we go. We give the ring carbon containing one of the substituents, either chloro group, the 1 designation. Okay? I'll choose that one. I don't have to. I could choose the other chloro group, or carbon connected to the chloro group, but it's going to come out the same way regardless. So I've given the ring carbon containing one of the substituents the 1 designation, and then I have to count around the ring the shortest distance to arrive at the other substituent. I would obviously just go 1 to the left. That makes it the 2 carbon. And then I count the rest of the way around the ring. Not that it matters, because there are no substituents attached to the 3, 4, 5, and 6. So it turns out that I have a chloro at the 1 carbon and the 2 carbon. So now all I have to do is, I have 2 chloros mean I have dichloro, and we write it as we did before. So these 2 chloro groups now become 1, 2 dash dichlorocyclohexane. 1, 2 dichlorocyclohexane. It's important to recognize that if we had these chloro substituents on different carbons, they would be named differently. And they'd have to be, because they are different compounds. So for instance, here are examples of 1, 3 dichlorocyclohexane and 1, 4 dichlorocyclohexane. Notice we would carry these out. We would name them in the same manner as we did 1, 2 dichlorocyclohexane. It's just that it's important to notice, and I just put all of these out there together, that we have 3 different compounds with 3 different names. If you have different compounds, you have to have at least slightly different names between them. Here's one to think about. Let's look at this very carefully. It's very important to recognize that a parent structure must be the one containing the greatest number of carbon atoms. Now, again, what's the parent structure on this? Well, we could start counting 1, 2, 3, 4, 5, 6, 7, 8, and we are doomed because we've counted into the ring. Remember, never ever count from the outside to the inside of a ring, or from the inside to the outside of a ring. We have to keep them separated. So we would say that we have a ring and we have a chain. That's the demarcation line. It's one or the other. And which one has the greatest number of carbons? Well, the cyclic component, that's a cyclohexane, so that has 6 carbons, but we would find that the linear portion has 1 more carbon than that, 7 carbons. It's a heptane, and thus that is the parent structure. More carbons wins, which makes the cyclohexane that we saw before, that's a substituent now, a substituent. We'll get to that. So we have to number this 7 carbon chain now such that the substituent has the lowest numerical designation. Well, there's 1 substituent. See that cyclohexane there? That has to be the 1 carbon. And we number from right to left because the 1 is the lowest numerical designation. Now, that whole cyclohexane ring is a substituent. And what did we say about substituents? Substituents had to have the suffix YL to show that they are secondary to the actual parent structure. So this would not be a cyclohexane substituent. It would be a cyclohexyl substituent. Very important. Cyclohexyl. And we see that that cyclohexyl now substituent is connected to the 1 carbon of the parent structure. Thus, 1 cyclohexyl heptane would be the proper name for this. Okay, let's go back to a structure that we looked at before. We had named this structure, if you remember, 1,2-dichlorocyclohexane. And I'm going to introduce now sort of a little idiosyncrasy with respect to cyclic alkanes. Cyclic alkanes. Now, alkanes having carbon-carbon single bonds can rotate around those single bonds. We have free rotation around them. However, when we take those carbon-carbon single bonds and we connect them into a cycle, they no longer have free rotation because they can't continually rotate because they're locked into a cycle. Now, this has connotations when we have 2 substituents on our cycloalkane. It gives rise to what are called geometric isomers. Let's tip this ring on its side to show that there are actually 2 different compounds that are named 1,2-dichlorocyclohexane. 2 different compounds with slightly different physical properties and so on. Let's tip this ring on its side to illustrate my point here. So here we have our ring tipped on the side. Notice that we have that bolded part sort of towards us, sort of wedged out towards us. So we can see it in sort of a 3D. And in a cyclic structure, there's a lot of hydrogen atoms on here. We'll just focus in red here on the chloro substituents. Notice on one way of drawing this, I have 2 chloro substituents here pointed down. And on the other way, I have a chloro on one side of the ring and a chloro on the other side of the ring. So when we go into a structure that is cyclic, we lock in an area which would be considered above the ring and below the ring. That's locked in now. We cannot take a substituent from the lower part, below a ring, for instance, and twiddle it such that that substituent could end up on the above side of the ring. We cannot do it. It is simply impossible because we've closed that single bonded alkane system into a cycle. So these are, what I'm showing you are 2 different compounds, but they seem like they're identical, don't they? They're not constitutional isomers of one another. Constitutional isomers were different compounds, but were related because they had the same molecular formula, but different connectivity. Here we have the same molecular formula on both of these, and we have the same connectivity. The same because we have these two chloro groups are on adjacent carbons to one another on both sides. So from the lens of a constitutional isomers, these would seem to be identical compounds, but clearly they're not. So we have to come up with another type of isomer to delineate that. And that is what these are known as geometric isomers, are pairs of compounds in this case. Geometric isomers have the same molecular formula, the same connectivity of atoms as we saw here, but different spatial orientations of the substituents. Notice in this case, here we have our two chloros, which are on adjacent carbons, but they're on the same side of the ring. Well, we have a name for that. That is, we call that, we put on a modifier called cis. If they're on the same side, we say cis. It is cis 1,2-dichlorocyclohexane. When we have the other sort of situation where there's two chloro groups on adjacent carbons, but they're on opposite sides of the ring, well, we could say that they are transposed from one another. And that brings us to the other modifier, trans 1,2-dichlorocyclohexane. Now, they're both 1,2-dichlorocyclohexane, but we have slightly different modifiers on there. Thankfully, because they have to be, the different structures must have different names. So if we have our two substituents on the same side of the ring, it's considered the cis geometric isomer. If the substituents are on the opposite side of the rings from one another, it is considered the trans geometric isomer. Now, in order to keep this learnable and not get too complex, I am only moving forward, if you're ever given to naming any of these, I am only going to be working with two substituents, not 3 or 4 or whatever, on a cyclic alkane structure, 2. And those two substituents, I'm always going to make them the same. 2 chloros, 2 methyls, 2 bromos, 2 ethyls, just makes it easier. Trans 1,2-di whatever, or cis 1,3-di whatever. So that's my promise to you, is to keep it learnable, to keep it somewhat brief, if this can be considered brief, I'm not, because it has the potential to get very complex very fast, and I want to keep this somewhat nerfed up a little bit. So before we go full in on bringing in these geometric isomers, the cis and trans terminology, into actual nomenclature, IUPAC nomenclature, we have to express a couple of ways of showing these, whether two substituents on a ring are cis or trans to one another. We can't always go with that three-dimensional sort of tipped up version that we saw before, where it was clear which one was on the top of the ring or the bottom of the ring and that sort of thing. That would get a little complex. But we have to be able to show, using pretty much a two-dimensional system, that three-dimensional sort of space. So there's two methodologies of expressing cis-trans geometric isomers in cycloalkanes. One is called the up-down methodology, where the substituents are disposed straight up or straight down off of a ring, or the dash wedge methodology, which perhaps you're a little bit more familiar with from perhaps looking in, remembering from general chemistry. Both of these are just as reasonable. Both of them are fine for expressing cis and trans. Let's take a look at the up-down methodology, how these things would be put forth. For instance, using our 1,2-dichlorocyclohexane analogy, this would be a way of expressing trans 1,2-dichlorocyclohexane. Notice that the two chloro groups are on adjacent carbons, as they must be if it's going to be 1,2, but one is pointing, the line is pointing straight down, and the line is pointing straight up. That would be a trans arrangement, or a trans geometric isomer, trans 1,2-dichlorocyclohexane, using that up-down methodology. The cis variant of this, where they're both on the same, expressed on the same side of the ring, could be shown in this case, the cis 1,2-dichlorocyclohexane. Notice they're both either pointed straight down, or we could draw them straight up. But they'd have to be, in this case, if they're 1,2, they have to be on adjacent carbons right next door, and they either have to be either straight up or straight down. Now, when I draw geometric isomers, I lean now away from the up-down methodology, although that's perfectly reasonable to do to show cis-trans, and I sort of go with the dash wedge methodology, where it's a two-dimensional way of showing or expressing three dimensions. A wedge sort of is drawn as implying coming out of the plane of the board, and a dash is implying moving into the plane of the board. Let's look at that with our model here, 1,2-dichlorocyclohexane. This would be a way now of showing what trans 1,2-dichlorocyclohexane using the dash wedge methodology. Notice, both those chloro groups are on adjacent carbons. That satisfies the 1, 2. But here we have one wedging, which means it's wedged towards us, and one dashed means it's away. That implies that one of those chloro groups is disposed to one side of the ring, and the other chloro group is disposed to the other side of the ring. Doesn't matter, and for our purposes, which one is wedged and which one is dashed. It's just that one is wedged and one is dashed. The cis variant would be either two wedges or two dashes, either way. Notice these two structures right here are exactly the same. If I took one of them and just turned it over, it would become the other one. So that's a little bit easier to see than on the up-down methodology from above, although on the up-down methodology, these again are the same compound, just different ways of rendering them. So now notice that we don't have to always be 1, 2. I'm sticking with that cis 1,2-dichlorocyclohexane idea, and we'll look at some examples moving forward how to name these. However, we could have them, don't have to have the substituents on adjacent carbons. They could be across the ring from one another. We saw an example of that. In this case, it would be 1, 4. But we always have to have this geometric isomerism in there if they're off of different carbons. Are they on the same side? Then it's cis. Are they on different sides? Then it's trans. The only time that we would have a di-substituted cycloalkane system that did not have cis and trans is if those two substituents were off of the same carbon. If two substituents are on the same carbon, there's no possibility for cis-trans geometric isomerism. In this case, this is a cyclobutane ring with two methyl groups off of the same carbon. It would be numbered as 1, 1 dimethyl cyclobutane, without putting cis or trans in there, because they must be across the ring from one another. Since there's only 4 bonds emanating from each carbon, they're all used up. There would be no way to have a cis variant of that with a trans variant, so we just throw away the idea of cis and trans if the two substituents are on the same carbon. So let's look at some examples. 2 shown here. The one on the top is a structure, and we are going to name this. The one on the bottom is a name, and we're going to draw the structure. Okay, here we have, the one on the top, the structure, what do we have as a parent structure? Well, in this case, it would be the only carbon architecture there, that 7-carbon ring. 7-carbon ring, which is a cycloheptane. Cycloheptane. And now, since there's 2 substituents on that ring, we have to number it such that one of the 2 substituents gets the number 1. Does not matter which. Then we have to count around the ring such that the next substituent, which is going to be the same, has the lowest numerical designation. I hope you'll see that we have to count around clockwise to get, so we have a 1-4 system right here. We can finish off that numbering if we want, but we have a 1-4 numbering system. And what are those substituents? Well, they're bromos, 2 bromos, dibromo. So we put this together. If we have a bromo at the 1 and a bromo at the 4, it is 1,4-dibromo cycloheptane. But notice what we put in here, this trans. That's sometimes forgotten. That trans, because the one bromo is pointed straight down and the other bromo is pointed straight up. That's the up-down methodology to discern trans geometric isomerism. So in this case, trans 1,4-dibromo cycloheptane. Let's look at the next one now. Cis 1,3-diethyl cyclopentane. So we have to draw that. Well, with these, again, we start at the very end. Start at the very end. Cyclopentane is going to be our parent structure. And there it is, cyclopentane. I drew that. And in this case, we see that we have to number our ring. Doesn't matter. We just number it from whatever carbon we want to, which is great. And we see that at the 1 and the 3 position, or carbon, there has to be each an ethyl group. We get that from 1,3 diethyl. There have to be. Importantly, we have to recognize cis right here, which means same side of the ring. Well, all right. I'll do the dash wedge terminology there. As I told you, I sort of favor that when I draw these things. I like dash wedge. I prefer it over the up-down methodology. But here, notice our 2 ethyl groups are drawn in so that we have 2 wedges coming out at the 1 and the 3 position. Understand, I could just as easily at the 1 and the 3 position draw 2 dashes at the proper positions. Doesn't matter one or the other, because in fact this and this are different renditions of exactly the same structure. It's just turned over from one to the other. Now notice when you're doing this dash wedge terminology, if we have a multiple carbon substituent, now notice in this case it is only that going from our parent structure to that first carbon where we have to wedge in this case, or dash in this case. Any other further carbons we draw just as lines. We don't have to have a continuous wedge or a continuous dash. It's just that first one that we see here. So practicing these are very important, and getting these as far as nomenclatures down. But as you can see, practice will make perfect on this. Just looking at these few examples probably isn't as much of a help as it could be, but you know, continuing working through these, whether it's naming them or looking at like something on the next slide, is very helpful. How about this one, friends and neighbors? Which of the following pairs are pairs of geometric isomers, pairs of identical compounds, or unrelated as either of the above? Okay, we have to carefully go through these. If we look at this first one over here, we can see, well, this is a 1,2-dibromo cyclohexane, both of them. But we'll notice that one of them is trans and one of them is cis. So on this one, and indeed on another one, let's look at actually the last one over here, we see it is both cyclohexanes, 1,2-dibromos, and they are, one is 2 wedges and one is a dash and a wedge. Those would be our geometric isomers. They have to be. Moving along, let's take a look at now, this one right here is an interesting pair, because essentially these are not rings. This is a linear compound, and so I've drawn these dashes and wedges, which I can, but they're really pointless, because in so doing, what I can do is if I look at one of these, and now I can rotate around one of these carbon-carbon single bonds, since it's not into a cycle anymore, and immediately I'll just rotate that up into this. So those would be identical compounds in that case, as would the pair over here on the right. These are just two ways of expressing the cis variant on this case. So it's at cis 1,2-dibromo cyclohexane. So these two would be identical compounds. Now, unrelated as either of the above, well, we have one left, so guess which one it's going to be. But it is important to look at immediately. Your eyes can cross sometimes, and if you don't look at this carefully, you can see, like, wait a minute, this is a 6-carbon ring. This is a 5-carbon ring. That's totally different. They're not even related. They don't even have the same molecular formula. So in this case, these would be completely unrelated as either of the above. It's important to take another look at these things sometimes with a fresh set of eyes can make all the difference.